Hello again. In this video lecture today, which is a sequence of our previous lecture, we will discuss about hypothesis testing. Remember, we discussed sampling distribution and some of the sampling distributions and some statistics, some sample statistics that can be used to test hypothesis for any parameter or any variable. So today we continue in this session with hypothesis testing. We will sketch some outline for how to test hypothesis, how to design a hypothesis, and what are the steps which one should follow to test any hypothesis. And in the end, we will work out with some examples so that we can understand the whole idea more clearly and more nicely. So let's continue. Well, since we are dealing with hypothesis testing, so I have a same quotation by Milton Friedman. The only relevant test of the validity of a hypothesis is comparison of its predictions with experience. Since we haven't experienced anything yet, and since we are completely relying on our statistical mathematical analysis based on data, so we should be holding our faith on the hypothesis testing. I discussed briefly in my previous session about steps required for hypothesis testing, but this part of the lecture will focus entirely on that. So hypothesis testing, the key elements to hypothesis testing are, so first of all, you design a hypothesis or you test or you set up a hypothesis which you wanted to test. For instance, if you remember from our previous session, we discussed about sampling mean being equal to population mean or sample proportion being equal to population proportion. In our future lectures, we will learn about some more, well, I don't say complicated, but some more important and some more somehow in-depth tests, such as not only looking for mean, but also looking for variances, for instance, and what are the tests which we can utilize for them. But right now, or up to now, we will only be focusing on mean and proportion. So whatever we are focusing among these two based on our data, we set up a design for that. We set up a test for that, a hypothesis for that. And then we decide the level of significance. Well, just to give you a bit of familiarity with this concept, level of significance is the probability of rejecting a null hypothesis when it is true. And we always want that probability to be small. Because if the hypothesis is true, there should not be a huge amount of probability or high amount of probability associated with that, right? Remember the concept of level of significance and also the confidence interval I said before in my previous lecture. And what is the confidence interval? I said I am 95% confidence that my sample or my population value will lie in this region. So if I say I'm 95% confidence about my hypothesis, it means there is something left over. Well, that 5% I'm slightly worrying about that due to some error or randomness. So that 5% is this level of significance. So 5% level of significance means I have set a probability of rejecting my hypothesis if I believe that this is true. And why I do that? Because of some randomness or data gathering, I said we may come up with some error. So we always, in statistics, we always provide a room for error. And the target is to reduce that error. We never said that there is no error. There is always an error. But the target is to reduce that error. Once we have set up hypothesis and decide about level of significance, then we choose a suitable test for that. If we are looking for mean, we choose a test for mean. If we are looking for proportion, we choose a test for proportion. And also, if you recall from our previous discussion, we also discussed two different tests like Z and T test. And based on the choice of data, based on the sample size, we can pick any one of these two. There are many other tests in statistics. We will not be only talking about these tests, But during the course of time, we will be discussing more. We will be learning more. I cannot put everything in this session right now, but I will distribute a piece of paper where you will see many different test statistics and when to use those test statistics. You don't need to remember those formulas by heart because everything is now available on internet, and well, most of the things actually, if not everything, or you can consult any of the books on statistics and you will find them very easily. So you don't need to remember them, just you need to remember the concept, when to use, what to use, and why to use. These are the things which you need to be familiar with. So we have decided about mean, difference in mean, proportion, then we chose appropriate test statistics, then we define a critical region. Well, that critical region is what we get from our tabulated or so to say theoretical values of the test. So just to give you a kind of recall, we discussed z alpha by 2 and t alpha by 2 in our previous sitting. I said the percentiles of z and t distributions. So these are the critical regions. They give us a critical region, and then based on that region we decide whether I am going to accept my hypothesis or I am going to reject my hypothesis. In examples, we will learn more about those critical regions. So please don't worry about it. Everything will be crystal clear when we will be working on examples or problems. Right now, I mean only to share with you a bit of flavor about theoretical setting of those statistical methods. In the end, we draw conclusion. As I said, whether I'm going to reject my hypothesis or I'm going to do not reject my hypothesis. These are the conclusions which we base about our analysis after doing following all these steps. We continue with some mathematical notations. So here is the step number 1. A hypothesis, again with some definition, if I say, is a statement about a population. Well, we are actually targeting population. We don't know population actually, but we are going to assess properties of population. But how do we do that? Well, we do by developing for the purpose of testing with sampled data. So we have a sampled data, and based on that sample data, somehow we develop statement about population. And there are some tests which we utilize in between, somehow to validate our hypothesis, somehow to provide some strength to our hypothesis about population, right? And in the step number 1, when we design our hypothesis, there are two types of hypotheses we make. The one is the null hypothesis, which says assume to be true unless there is sufficient evidence to the contrary. So say that population sample mean is equal to population mean, or population mean is equal to sample mean. This is the null hypothesis. This is true, right? And alternative is test against the null. If there is evidence that H0 is false, we accept H1. Of course, there are two alternatives. So if one is failing, then other one we are going to accept that. So if I say that my population mean is equal to sample mean, this is my null hypothesis, because this is what I am going to aim to check. This I am sure about. But if this is not true, then what is true? The true is that they are not equal. So population mean is not equal to sample mean. This is our alternative hypothesis. Sometimes we do know about some specifications, like if population mean is not equal to sample mean, right? It is also possible that the population mean is greater than sample mean. And it is also possible even that population mean is smaller than sample mean. So sometimes we do know those specifications. But if we do not know anything about these specifications, we just say that it's not equal, right? To be on a safer side. And we discuss if we have these three specifications like greater than, equal, or not equal, what or greater than, less than, or not equal, what kind of implications it can have on our test statistics and also on our decisions. Step number 2, select a level of significance. Well, I said 5% is a standard criteria that alpha, we notify this this by a mathematical notation alpha. We say alpha equals to 0.05, and it means that I'm 5% or I'm 95% confident about my test. or about my hypothesis, actually, not the test. Then we compute an appropriate test statistic, whether it's a Z or T, and also whether it's about mean or proportion or difference of means, for instance. Once we have defined the appropriate test statistic, then we decide or design a decision rule. And the decision rule says reject the null hypothesis if the critical value means the test statistic value, is greater than the tabulated value. So if that value lies over the region of tabulated value, then we say that, okay, we are going to reject our hypothesis. Once everything is done, then we make decision via computing the p-value. Well, the p-value is defined as the smallest significance level at which a null hypothesis can be rejected. So we calculate, we say that, okay, alpha is not, well, our hypothesis is true, and I'm 95% confidence about my hypothesis. I have 95% confidence on my hypothesis, and my alpha is 0.05. So I'm not going to reject. So we sometimes calculate what probability is required to reject that hypothesis, that true hypothesis. So we calculate p-value. That p-value is the probability of actually rejecting the true hypothesis. And if that p-value, now just listen to me very carefully, if that p-value, which is the probability of actually, or the smallest probability of actually rejecting the true hypothesis, if that p-value is less than alpha, then we reject our hypothesis. And if this p-value is greater than alpha, then we do not reject our hypothesis. Now we move on. There are two types of errors we can make when we are working with hypothesis testing. Type 1 error and type 2 error. That's what we use in statistical books, standard statistical books. These are the notations. You should remember that. What type 1 error is: rejecting a true H0, rejecting a true null hypothesis is type 1 error. You are rejecting something when it is true. It's an error, right? You should not be rejecting something when it is true. But sometimes we do reject something when it is true based on our evidence. We do not have enough evidence to somehow validate our assertion or hypothesis. Type 2 error is the another type of error, and that error occurs when we do not reject our wrong hypothesis. So, and this is also an error. We should not we should be rejecting our false hypothesis, right? But sometimes we do not have enough evidence. By evidence I mean enough data, right? We are dealing with data. Our evidence is data. Statistics, quantitative analysis, completely based on evidences, and that evidence, by that evidence we always mean data. And that what we call another type of error. So we usually notify them by a mathematical notation alpha and beta. Notice that alpha is similar as the level of significance here. So if you look at this small matrix, you see that when H0 is true and when you reject H0, this is type 1 error. When H0 is false and you reject H0, it's a correct rejection. There is no error in that. When H0 is true and you fail to reject, it's also a correct decision, because that you shouldn't be doing. And also if H0 finally, if H0 is false and you fail to reject, it is an error, right? So that's how we define in a matrix form both of these two errors. Well, I said significance level, probability of rejecting a null hypothesis when it is true, of course. This gives us a type 1 error. This is what we call as alpha. Power of a test is very important. Whenever we make a test to test a hypothesis, we calculate the power and size of the test. So if power and size of the test are good, then we say that that test is strong. So power of the test is the probability of rejecting a null hypothesis that is false. So how strong the power of your test is, it means how strong it can react to reject a hypothesis when it is false. So the false hypotheses are more important to us than a true hypothesis being rejected. And when we will be discussing about data, or when we meet in a meeting session, I will give you some more examples why this false hypothesis is more important to reject than rejecting a true hypothesis. And the power of the test, we usually notify them by 1 minus beta. P-value, as I said before, I give you a brief somehow definition of that quantity, too important in a statistical analysis. It is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that null hypothesis is true. It is the observed level of significance. So when testing a hypothesis, we state alpha, we calculate p-value, and if p-value is less than equal to alpha, as I said before, then we reject H naught. And if p-value is if not less than equal to alpha or bigger than alpha, then we do not reject our hypothesis. So just remember that the p-value is the smallest significance level at which the null hypothesis can be rejected. So we need to calculate what value is required for the hypothesis to be rejected. What is the probability? Well, not value, but what is the probabilistic value, so to say, is required, the smallest probabilistic value, smallest probability attached to it when a null hypothesis can be rejected. So since we have already set alpha, so we calculate p, and then we compare those two values and then decide. So let's see some examples here. Well, I do not have solutions to those examples right now. I would be gladly happy to work on whiteboard so that we can discuss and also understand them very clearly. But right now I have put some statements to you. And if you want, you can think about how you can approach solving those problems by your own. So here is a problem testing for a population mean. We wanted to test the population mean based on our data on samples. So the mean annual turnover rate of the 200 count bottle of Bayer aspirin was reported to be 6 times per year. So the mean of 200 bottles is 6 times per year. And how many bottles we have? Well, we have 200 bottles. It means n, small n, is 200. The mean value is 6, and the standard deviation is 0.5, right? And well, this is the information given to us. But what we wanted to test? Well, we wanted to test that it is suspected that the mean turnover rate has changed and it is not 6. Test all hypotheses at alpha equals to 0.05 level. So now you have n, which is given to 200. You have x bar, which is 6. You have s or sigma, well, based on sample or population, which is 5. And you wanted to test your hypothesis. So you have all the quantities. And since your n is too large, we will go for z test, right? And then we plug in all the values in the z statistic. We wanted to test whether x or mu equals to 6, which is our null hypothesis, and mu is not equal to 6, as I mentioned here, which is our alternative hypothesis. So we plug in all those values there, we calculate the test statistics, and then we compare our critical value obtained from the test statistics using the tabulated value, which is the percentile of z. And then we decide, are we going to reject or not? Sometime we do have some information about a small sample. Said a random sample of n equals to 64 bottles showed a mean of x bar equals to 5.84. Should we reject the null or not? So now instead of 200 bottles, we have 64 bottles. So instead of looking for population, we have a sample. And we wanted to assess population based on that sample. So we plug in all those values now from the sample in our statistic and try to assess our population. Right? So think about this example, and we will be working on that in our meeting session, hopefully. Small sample problems. So here is another example. It says the claims department at McFarland Insurance reports that the mean cost to process a claim is $60. So mean cost to process a claim is $60. It means this is the mean value, right? After implementing some cost-cutting measures, McFarland selected a random sample of 26 claims. Well, when I say random samples, just notice that this is a small n. And found that the sample mean X bar was $57 and the standard deviation was 10. Since we are talking about samples, so this is S. Remember, the population mean was $60 since we were talking about a general claim from that company. But once we gathered the data, sampled the data of 26 claims, we noticed that the mean was 57 and the small standard deviation was 10, right? Question of concern is at the 1% level, alpha equals to 0.01, are the cost cutting measures actually reducing cost or not? So since we have n equals to 26, which is less than 30, and we have information from sample like sample mean and sample standard deviation, we will immediately start with t statistic. Plug in all the values, calculate those values, and then compare with the tabulated value to decide, are we going to reject that hypothesis or are we not going to reject that hypothesis? Again, think about this problem from the mathematical perspective we discussed earlier and also in this session, and just formulate your answer or your solution about this problem. We move on. Testing for proportions. So now here in this example, an airline company claims that 78.4% of their arrivals are on time. So this is a general claim. It means this is the population mean, right? Whenever we claim something, generally we say that this is about a population. But when we pick some samples and start looking into that sample, then we say, okay, this is now we are working with samples. However, recent data indicates that out of 750 flights, now this 750 flights means sample because airline companies do not deal with 750 flights only, they deal with many flights. So since this is a small number compared to their general structure, so we say that this is a sample mean, a sample value of that from that airline company. Now it says that out of 750, 630 are on time. Does this data support their claim? Now remember the probability of success and probability of failure. So we remember when we were discussing about that concept, we said that okay, we will gather some data and we decide our interest and we calculate or we count how many times our interested outcome appears, right? And that was the probability of success. That was the proportion of success. So in this example, we have n, small n, which is 750, and out of 750, 630 times flights were on time. So 630 was our success. So what we will do, we will just divide 630 from 750 and then we will get a proportion. So we divide 630 number of flights which were on time by 750, the total number of flights, and we will get a proportion P. And we also know, well, this will be P hat, by the way, because we are dealing with samples. And we also know what the actual P from the population, and that actual P was 78.4%, right? So now we have all those measures and we plug into the suitable test which we discussed in our previous session, in our previous presentation. So, and we can assess, are we going to reject that hypothesis or are we not going to reject our hypothesis? So just think about this problem and also mathematical formula, try to plug in, do something, try to solve. Do not always expect correct solution or correct result. We can try and then we learn. So try that, and when, as I said, when we meet, we will be solving this on whiteboard for our understanding, and we will be discussing. But it will be good if you try before our final discussion, so that you can understand or you can see where you lack actually. Sometimes we compare two means. Sometimes we are not only interested in one sample, sometimes we are interested in two samples and we wanted to compare them together. Somehow we compare their means together. Like here, Wall Street Journal runs a contest comparing the performance of stocks. So Wall Street Journal is a very famous journal, is a famous newspaper on financial news or financial updates from US. They want to compare performance of various stocks, say two stocks. Half are chosen by expert and the other by throwing darts at the stock listings. So half of them are chosen by experts and half of them are chosen through some experiment. So this is also an example of like observational study and also the designed study, so to say. Here we have both of those outcomes, or outcomes from both of these experiments, so to say. From the experts, X is equal to 11.6% and standard deviation was 22.4%, while for the darts, Y is 6.5% and standard deviation was 22.8%. So there are at least two ways to test this hypothesis. One can solve this problem by at least two ways. And one of the way is matched pair. If each data series, well, there is a distinction between those two definitions, and this tells us which method we should use and when we should use which method. So like matched pairs is one of the ways, and it says if each data series can be matched by the date in which it's selected. So if you have two observations at the same date and this keep going on, then you can compare them as a matched pairs. Then we can use the difference in data series, the DI, the difference of data series, we notify them as DI. And this approach can be used if two data points were selected at the same date. You understand me? But if data are not matched, like if they are not sampled or if they are not notified or selected at the same date, at the same point, so they can be considered as two independent samples, like they are not depending on one another, right? They are not obtained at the same position. They are independent. Then we use two sample test to compare two groups. So right now in this example, since we have, we will see what type of example we have right now. We have data or information about that example where both of those experts or DART experiments were done at the same date. So we will apply the DI approach. But if we do not have that case, then we go for two sample test. And I'm not going into detail about the mathematical structure of those two tests, but when we meet next time, hopefully I will share you something. As I said before, I don't want you to overwhelm with lots of mathematical notations and lots of tests actually regarding this topic, but it's good to know the concept. It's good to be familiar with the understanding of the concept. And once you know the concept, you can pick any suitable test, any appropriate test, and those tests can be accessed from any book or on internet as well. There are lots of materials available, so you don't need to remember them by heart. And also when we will be working on SPSS, we are not going to plug in formulas over there. SPSS will built in, SPSS will do the job for us. We just need to choose an appropriate, somehow appropriate command or appropriate tool to do that job. So most important to us is the understanding, not the remembrance of the mathematical formula, right? So here is the data, and you said that, well, we have a period of say 120 observations from June 1990 to May 2000, and experts have chosen some values and DART board have chosen some values on the same date. Some of the days we do not have values, so we will just discard them, but the rest we can consider. So in the next session, when we will be working on whiteboard, hopefully, I will try to solve this problem before you, so that we see how can we use those mathematical notations or tests in practical problems. So please listen to all those lectures which we have uploaded so far, and make note of things which are bothering you. Try to understand concept. Try to solve these problems as I shown here in this as I've shown this in the slide. Try to solve them. Think a bit about, and when we are going to meet, we will be discussing more about them. Yeah. So good luck and see you soon. Thank you very much.